Welcome to A-Level and AP Physics. In today's lesson, we will try to discuss all possible graph questions from nuclear physics. In the last video, we have already discussed all possible graphs from quantum physics. And we will discuss these questions in detail so you can improve your conceptual understanding of this topic, and also you can have better understanding of graph related questions. Let's study together. Let's improve together. Question 9 part A says an isotope of an element is radioactive. Explain what is meant by radioactive decay. Radioactive decay is simply a name of process in which an unstable nucleus emits alpha, beta or gamma radiations to become a stable nucleus. And it emits alpha, beta and gamma radiations randomly and spontaneously. And this process we call is radioactive decay. Let's try to understand this one in a proper way. Imagine that we have unstable nucleus. So simply we can write on we have unstable nucleus. This nucleus can become stable nucleus by emitting alpha particles or by emitting beta particles or by emitting gamma radiations spontaneously and randomly. So we will call this process radioactive decay. So let me show you the answer, how you can write down your answer. So this is how you can write down your answer. In your answer you can say, during radioactive decay, the unstable nuclei release alpha particles, beta particles or gamma ray randomly and spontaneously to become more stable nuclei. So randomly and spontaneously are very important because radioactive decays are random in nature and also spontaneous in nature. So you have to mention this one in your answer, then you can get 3 marks for this question. Part B says at time t, a sample of radioactive isotope contains capital N nuclei. In a short time delta t, the number of nuclei that decay is delta n. State expressions in terms of symbols t, delta t, capital N and delta n for the number of undecayed nuclei at time t plus delta t. So for this question it is given to us at time t, we have number of nuclei that is equal to n. So we can say number of nuclei. So we have number of nuclei that is equal to capital N. Question is, and it is also given to us that in time delta t, the number of nuclei decayed. So we can say decayed nuclei in delta t, decayed nuclei in time delta t. So how many have been decayed? That is equal to delta n. Now question is asking us at time t plus delta t, undecayed nuclei. At t plus delta t, we need to write down undecayed nuclei. We need to find out undecayed nuclei. So this is simply n minus delta n. So we have n minus delta n. Because delta n has been decayed and initially we have n, so n minus delta n. This is number of undecayed nuclei. So simply we can say n minus delta n. For the second part, question is asking us to write down the mean activity of the sample during the time delta t. Activity is the number of nuclei decayed per unit time. So activity, we can say this is equal to decayed nuclei. So simply we can say this is equal to decayed nuclei. So this is equal to decayed nuclei over time taken. So decayed nuclei we have that is equal to delta n. So activity is simply equal to delta n divided by time taken, that is delta t. So we can write on this. Next one is the probability of decay of a nucleus during the time interval delta t. And probability, this is equal to success over sample. Success means the number of nuclei decayed. In this case, number of nuclei decayed, we have delta n. delta n has been decayed, and the initial number of nuclei in the sample initially we have capital N. So this one is the probability of decay of a nucleus. Next one is decay constant. Decay constant, we use symbol for this one, lambda. This is probability of decaying per unit time. So this is the probability of decaying of a particular nucleus, of decaying of a particular nucleus per unit time, or in any given time, per unit time. Probability of decaying of a nucleus per unit time, probability of decaying. So we already have the probability, we have calculated. This is delta n by n. So this is the probability, and this one has to be divided by delta t in given time. So simply we can say this is equal to delta n by n multiplied by 1 over delta t. So this is how we can write down decay constant. Part C says the variation with time t of the activity capital A of a sample of a radioactive isotope is shown in figure 9.1. If you look at figure 9.1, we have activity on y-axis and we have time on x-axis. And if you look at this one carefully, we can see after one half-life, activity becomes half, means activity here, this is equal to A by 2. And after another half-life, activity again becomes half of the previous activity. So this activity will be equal to A by 4, means half of this one. We can also say this one is the initial activity. We can say this is A0, and after one half-life we have activity A1. After another half-life we have this is activity A2, and after another half-life we have activity A3. This will be half of this, so this will be simply equal to A by 8. So this is how activity is decreasing. But for this question, we have to sketch a graph between N and T. If you read this question, it is given to us the radioactive isotope decays to form a stable isotope capital S. At time T is equal to 0, there are no nuclei of S in the sample. On the axis of figure 9.2, sketch a graph to show the variation with time T of the number n of nuclei of S in the sample. So we need to sketch a graph to show how number of nuclei of S increase with time. In order to understand the relationship between A and N is the number of nuclei. So simply we need to understand that A is equal to lambda times N. N is representing number of nuclei of daughter nucleus, of daughter product. So from here we can say A is directly proportional to N. So it simply means that when A is half, N is also half, and vice versa is also true, and so on we can simply say. So when this is A by 4, this is 1/4, this also has to be 1/4. Now let's try to understand how parent nuclei and daughter nuclei, they are linked with each other. Imagine that we have X isotope. It has 100 nuclei. After one half-life, so we can say after one half-life T 1 by 2, they become half. So simply we will have 50 nuclei of X and we will have 50 nuclei of S. And after another half-life, this 50 again divided into 2. So first of all we have here, so we have this is 25. Now 50 become half, we have 25x, so this become 25s, and this one we have 50s. So now we have 75 and so on. And if you write on one more step, means after another half-life, so we can say here after another half-life. So now in this case, this 25 will be divided again by 2. So we will have here 12.5 nuclei of X, and rest of them, they will be X. so this will be X. So we will have about 87.5 S. So these nuclei S. Let's try to understand a little bit more about S, how number of S nuclei are increasing with time. So here if we look at number of nuclei of S, we have 0 nuclei, and after one half-life we have 50 nuclei of S. So we can say S is equal to 50, and after two half-lives we have number of nuclei of S, that is equal to 75, and after three half-lives we have number of nuclei of S, that is equal to 87.5. We can say this is S naught, the initial number of nuclei, and this is after one half-life, this is after two half-lives, and this is after three half-lives. But the proper way to represent this one is we can express this one in terms of percentage. So initially we have 0%, then we have 50%, then we have 75%, then we have 87.5% after three half-lives. So we can also label here. So we have 25% on this axis, here we will have 50%, here we will have 75%, and here we will have 100% number of nuclei in the sample. So first of all we have 0, so we can use one dot here. After one half-life we have 50%, after two half-life we have 75%, and after three half-lives we have 87.5%. Now simply we have to connect these points. So we can draw this exponential growth curve like this. So this is how you need to sketch the graph. I hope this one is clear to you. Let me show you a better one. Let me show you the better one, a proper graph. So this is how you can sketch a proper one. So let me clean this part here with percentage, you can see. So this is how you need to sketch the graph. For the sake of this question, simply what you need to do is you need to simply sketch this graph. Rest of the things are for your understanding. Why do we sketch like this? I hope this one is clear to you. Question 2 part C says a pure sample of radioactive isotope contains N naught nuclei. The half-life of the isotope is T sub half. The product of the radioactive decay is stable. The variation with time T of the number N of nuclei of the radioactive isotope is shown in figure 5.3. So this is for radioactive isotope, this curve. On figure 5.3, label on the time axis the time T is equal to 1.0 half-life and T is equal to 2 half-lives. Sketch the variation with time T of the number of nuclei of the decay product for time T is equal to 0 to T is equal to capital T, means until this time. So we need to sketch for decay product. Now the same concept. So if you look at this radioactive isotope, we can see N becomes half. N becomes half after one half-life. So first of all we can label here. Here is 1 half-life. So this is 1 half-life. So here we have 2 half-lives. So this time will be equal to 2 half-lives, and this time this will be equal to 3 half-lives. So this is first of all how we can label. Now when radioactive isotope, number of nuclei of radioactive isotopes become half, number of nuclei of decay product also become half, means become 50%. So here become 50%, and now here we have 25% of nuclei of radioactive isotope. So we will have 75 of decay product, and again it become half, so it will be halfway here. So 1 2 3 4 5. So simply 1 2, so we have 1 2 3 4 5 here. Now simply we need to connect these dots and curve for the decay product. That will be just reflection of this curve, just reflection. So let me connect these dots. So if we connect them like this. So this is just reflection. Now let me show you the better one, how you can sketch a better one. So this is how you can sketch a better one. This is what you need to sketch in your exam. So we can clean the previous one. So this is how you can sketch just reflection. And this graph is a typical graph. You will see in lot of past papers, always they're asking you about this exponential growth graph. And so this is how you need to sketch. So let me highlight one point. This is for radioactive isotope. So this is for radioactive isotope. Just label this one. And this is for decay product. Decay product. Decay product is stable. This one is stable, but this one is unstable. Unstable. So this is all what you need to do for this question. Question 13, part A says, explain what is meant by gamma radiation. Gamma radiation is simply electromagnetic wave emitted by decaying nuclei. Emitted by decaying nuclei. When unstable nuclei become stable nuclei, they emit alpha, beta, and gamma radiations. And gamma radiation is one type of nuclear radiation that is emitted during radioactive decay. Now let me show you how you can write down your answer. For the sake of answer of this question, simply you can write down is an electromagnetic wave. If you mention this one, you will get 1 mark. And then if you have mentioned it is emitted from a decaying nuclei, you will get another mark. So you will get 2 marks for this question. Question B says, a source of gamma radiation is placed a fixed distance away from a detector and counter as illustrated in figure 13.1. A sheet of lead of thickness X is placed between the source and the detector. Between the source and the detector. The average count rate, capital C, corrected for background is recorded. This is repeated for different values of X. The variation with thickness X of ln C is shown in figure 13.2. Here we have figure 13.2. So this is figure 13.2. If you look at this figure carefully, on y-axis we have ln of capital C, means ln of average count rate, and on x-axis we have value of thickness. This is given in millimeters. In the next part, actually we need to calculate the gradient of the graph. So first of all, we will draw a best fit line. So this is how you can draw the best fit line. So you can see in this best fit line, we have the same number of dots. We have 1 dot, this is below this best fit line, and this 1 dot is above this best fit line, and the distance from the line is almost same. And if you look at this point, this is below this best fit line, and its distance from the line and the distance of this point from the best fit line is also the same. It means this line fit all the points. So this is our best fit line. Now we will go to the next part and we will try to answer the next question. If you look at this question, for this question it is given to us that the absorption of gamma radiation in lead may be represented by this equation, where C0 is the count rate for X is equal to 0 and mu is the linear attenuation coefficient. Use figure 13.2 to determine the linear attenuation coefficient mu for this gamma radiation in lead. So we have to determine the value of mu. Mu is given here, so here is mu. But if you look at this figure, we have ln of C on y-axis. So it means we have to take ln on both sides. So we will write down C is equal to C0 e to the power of negative mu x. So this is typical exponential curve, equation for exponential curve. Now if you take ln on both sides, we can say this is ln of C. This one will be equal to ln of C0 minus we have mu x ln of E. But ln of E, this is equal to 1. Ln of E, this is equal to 1. So simply we can write down, we have ln of c, this is equal to negative mu x plus we have ln of c naught. Now we can compare this one with straight line equation. Y is equal to mx plus c. So in this case, gradient is equal to negative mu and y-intercept is equal to ln c, means you can find the value of ln c naught from here. So we can say in this case, gradient, this is equal to negative mu. So this is equal to negative mu. First of all, we can say this is equal to negative mu, and we can say mu is equal to negative of gradient. So this is the point you need to understand. We will calculate the gradient and then we will take negative of gradient, that is value of mu. So mu will be positive in this case. So now simply we can take 2 points on this one. We can take 1 point here, so we will be taking 1 point here and we will be taking another point here. So we have taken these 2 points. Maybe these 2 points are very small to see, but I'll be writing the coordinates here. So we have coordinates of this one, that is 2.4 comma we have 3.75, and coordinates of these points we have, this is 14.4 comma we have 3, this is here. Now we need to calculate the gradient of this one, so we can calculate gradient. So we have this point. First of all, we have 3 minus 3.75 and this is divided by 14.4 minus we have 2.4. If we solve this one, we will get negative 0.0625 up to 2SF. We can write down this is 0.063. So this is the gradient and this is negative, so gradient is equal to this one. So we can say gradient. So the mu in this case, mu will be equal to 0.063 per millimeter, because log of any quantity, it has no unit. Log of any quantity, it has no unit. So the answer for this one is 0.063 per millimeter. So this is the answer. In the mark scheme, given answer for mu is 0.061 per millimeter plus minus 0.004, and our answer is in this range. So this is how you can figure out value of mu. Part C says the value of mu calculated in B is for gamma radiations in lead. Suggest and explain whether the value of mu for aluminium would be the same, greater or smaller. Suggest and explain. So we need to understand, if we pass gamma radiations through lead and we pass gamma radiations through aluminium, in which metal gamma radiations are more absorbed? So simply I hope you will say gamma radiations are easily absorbed by lead, means lead will absorb more gamma radiations, and aluminium, it will absorb less. So we can say aluminium. So here we have aluminium and here we have lead. Aluminium absorb less, it will absorb less, and this absorb more. So we can say absorb more. If it absorb more, it means mu will be greater for this one and mu for this one will be less. So we will simply say mu for aluminium, it has to be smaller as compared with mu for lead, means for PB. So if mu is smaller, it means the gradient. So we can say the gradient. So gradient for aluminium also has to be shallower as compared with gradient for lead. So that's all what you need to understand. lead is very good at absorbing gamma radiations, but aluminium is less absorbing. So the value of mu for aluminium will be smaller, and mu is equal to negative of gradient. So the gradient of the graph also will be smaller. So if these points are clear to you, now let me show you how you can write down your answer. In your answer, you have to mention these points. Aluminium is less absorbing compared to lead. Gradient of the graph will be smaller, hence a smaller value of mu. Part C says a radioactive isotope decays with a half-life of 15 seconds to form a stable product. A fresh sample of the radioactive isotope with time t is equal to 0 contains n naught nuclei and no nuclei of the stable product. On figure 6.3, sketch the variation with time t of the number n of nuclei of the stable product. For time t is equal to 0 to t is equal to 45 seconds. Half-life is given to us, half-life of radioactive isotope, that is equal to 15 seconds, and we need to sketch from t is equal to 0 to t is equal to 45 seconds. It means we have 3 half-lives. So we are talking about stable product in this case. Stable. We are talking about stable product. Stable product, initially it has no number of nuclei, so initially it has n that is equal to 0, and after one half-life n will increase to 0.5 n naught after one half-life, and after another half-life this will be equal to 0.75 n naught, and after another half-life this one will be equal to 0.875 n naught. So this is after one half-life, t1 by 2, and this is after 2 t1 by 2, and this is after 3 half-lives. So this is after 15 seconds, this one will be after 30 seconds, and this will be after 40 seconds. Now simply we need to label these points. So first of all we have 0.5, so after one half-life we will have 0.5, and after 2 half-lives we will have 0.75, and after 3 half-lives we will have 0.875. So 1 2 3 4 5 means half of that every time. So half of this one, half of this. Now simply we need to sketch this one, so we need to connect these dots. So this is growth graph, so exponential growth graph, the shape will look like this. So this is how you need to sketch. It's a typical type of question, so you need to read question carefully. You need to sketch graph for the stable product, or you need to sketch graph for radioactive isotope. So this is for stable, so it means this is growth graph. So this has to be growth graph. So this point you need to understand. If question asks you to sketch for radioactive isotope, it has to be decay graph. So it has to be decay graph. Decay. This is decay, this one is growth. Let me show you the proper graph how you need to sketch. So this is how you need to sketch a proper one. Let me clean this. So this is how you need to sketch. If you wanna label this, we can also label. This will be 0.75 and this will be 0.875. And that's all for nuclear physics. I hope you have better understanding of nuclear physics. And for quantum physics, you can check part 1. In part 1 we have already discussed about graphs for quantum physics, and you can find all the possible graphs for quantum physics in part 1.